Welcome to lecture number 5 for ECE 463 Modern Control, Canonical Forms, and Similarity. Now, here's kind of interesting observation. Given a generic fourth order system like so, I've got 8 degrees of freedom. There's your 1, 2, 3, 4 in the numerator, 1, 2, 3, 4 in the denominator. If I represent this in state space form, I actually have 25 degrees of freedom. This is a fourth order system, so A is a 4 by 4 matrix, that's 16. B is a 4 by 1 matrix, C is a 1 by 4, D is a 1 by 1. Altogether, I've got 25 degrees of freedom. With 25 degrees of freedom and 8 constraints, there's an infinite number of solutions. They're all perfectly valid ways of representing the system. They're just different ways of doing it. Well, of those infinite number of solutions, some of them have names. Those are canonical forms. Many do not. And they're all related. They're related by a thing called a change in variable or a similarity transform. That's what we're going to talk about today. Some canonical forms that have names and some properties they have, as well as how to convert from one to the other. So let's start with controller canonical form. So if I have a generic transform, say of this form, to get a controller canonical form, do the following trick. First, let's define a dummy variable x. X is just 1 over the denominator polynomial. Then y is the numerator polynomial times x. Now you might think I'm going to have to start differentiating because I have all these s cubes, s squared, s in there. Actually you don't. The fact that you don't is very, very good. Differentiation is a noise amplifier. If there's any noise on the system and I differentiate it, I'll just get, pure crap. So being able to implement a transfer function with zeros without differentiating is really important, and you can do that. You'll see that in just a sec. So to convert to controller canonical form, I've got this dummy variable x is 1 over the denominator polynomial times u. Cross multiply and solve for the highest derivative of x. That gives you s to the fourth x is equal to u minus, because I'll take these terms, bring them right, using the minus sign, minus b3 s cubed x, b2 s b1 b0 x. Now if I have the fourth derivative of x, I can generate the third, second, first, and 0th derivative by integrating. So here take the fourth derivative of x, integrate once, twice, 3 times, 4 times, and I have all the different states. The reason I integrate is integration actually cleans up signals. If I have noise, noise is typically high frequencies. Integrators clean up noise. The high frequency gain is 0 or small, so this will help filter out or clean up the signals. Versus if I use differentiators, I would just make things worse. So this is actually a practical solution. Now I can use this equation right here. Given x to the fourth and its integrals, or integrands, this tells me how the fourth derivative of x is related to the lower derivatives. And I can do that as follows. I'll create the fourth derivative of x as the sum of u minus b0x minus b1x prime minus b2x double prime minus b3x triple prime. So this block diagram is a way to implement that differential equation. Now if I look at the numerator polynomial tells me how x's combine to create y. So what I'll do is I'll take the different terms, x times a0 plus x prime times a1 plus x double prime times a2, and so on. Add them all up, I get y. So this block diagram is one way to implement this transfer function. And this is called controller canonical form. The reason for that is if I take the input and make that a delta function, at t equals 0, I just defined what x4 is. If I make that a doublet, derivative of delta, I've changed x3, and so on. From the input, I can control what all the states are. Hence the name controller canonical form. To put that in state space form, define the output of the integrators to be your states. I'll call this x1, x2, x3, x4. Then it'll look like this in state space form. The integral of x2 is x1. The derivative of x1 is x2. That's what this says. The derivative of x1 is the second state, x2. x2 is the integral of x3. The derivative of x2 is x3. Correction. x2 is the integral of x3. x3 is the derivative of x2. So the derivative of x2 is x3. The derivative of x3 is x4. Again, going left to right is integrate. Going right to left is differentiate. So that's what this upper part tells you. I just have 4 cascaded integrators. The poles, the transfer function, and the denominator shows up in this bottom row. The derivative of x4 is minus b3x4 minus b2x3 minus b1x2 minus b0x. So here's all these terms plus u. The output then is your numerator polynomial times your 4 states. a0 times x1 plus a1 times x2 plus a2 times x3 and so on. The nice thing about controller canonical form is it's really easy getting into. If I know the transfer function, I can write the state space model by inspection. This is 1 on the op diagonals, meaning a bunch of cascaded integrators. B matrix is 0, 0, 0, 1. This bottom row is minus the denominator polynomial. The C matrix is the numerator polynomial. So this is really easy putting in state space or in controller canonical form. Likewise, many programs, some of the earlier versions of MATLAB did this automatically. If I go from transfer function, MATLAB has to store the transfer function somehow. It stores it in state space form. And kind of figures somebody had to write the MATLAB code, SS or TF. This is an easy way to do it. The problem with controller canonical form is while it's the easiest form to get into, it has the absolute worst numerical properties. The reason for that is suppose I have 4 poles at minus 10. This last term will be 10 to the 4th. This is going to be 40. When you have such a big spread, 10 to the 4th and 40, you start getting numerical problems. But it's easy to get into, and if you're using extended double precision mathematics, it usually works, as long as you keep the poles close to 1. But that's controller form. There are other forms. One is called observer canonical form. So again, given the same system, x dot equals ax plus bu, y equals cx plus du, if you find the transfer function is going to be solved for x, gives you x, bring the a left, take the inverse of si minus a times b, substitute. Here's the transfer function. If you have a single input, single output system, and I transpose it, the transpose of a scalar is still a scalar, has no effect. If I transpose it, it's still a perfectly valid transfer function. However, what I wind up with is B transpose, Si minus A transpose, C transpose plus D transpose. So these are both representations of the same system. What that means, if I substitute B transpose for C, A transpose, C transpose for B, and D transpose for D, I'll have exactly the same transfer function, just a different canonical form. That'll be called observer canonical. As an example, take that controller form that we had before, have A go to A transpose, so instead of the B's being on the bottom, they get transposed, wind up on the right. C transpose becomes B, B transpose becomes C, D transpose is D. This is exactly the same system, exactly the same transfer function, just a new canonical form. If you draw the block diagram of it, it looks like the following. So if we look at the first one, x1 dot is minus b0 x4 plus a0 u. So x1 dot right here is a0 u minus b0 x4. x2 dot is x1 minus b1 x4 plus a1u. So x2 dot right here is minus b1 times x4 plus x1 plus a1 times u, and so on. This is a case where it illustrates you don't really need to differentiate. You might think I need to differentiate u because this a1s term, and actually I don't. if I differentiated u and fed it in over here, I would differentiate it, then integrate it. Integration is the opposite of differentiation. They undo each other. So rather than differentiate in here, a2 is times the second derivative of u. If I take the second derivative, integrate twice, I'm back where I started. So I'll just pre-apply u to the third integrator times a2, and likewise for a4 or a3. Likewise, I don't ever have to differentiate u. I can just do that trick and decide which integrator I feed it into, and the net effect is this has the transfer function with a0 times u, a1 times su, even though there is no s, a2 times s squared u, a3 times s cubed u. Thus I've implemented s's in the numerator without actually differentiating. And again, that's very, very good. This is called observer canonical form because from the output, I can determine what the states are. For example, suppose u equals 0. If I take y and differentiate it, I get x3. Take the second derivative, that's x2. Third derivative is x1. So just by looking at y and its derivatives, I can tell you what the states are. Hence, it's observable from the output. Third form, Cascade Form. In Cascade Form, if you have real poles, I can factor the system, factor the denominator polynomial as follows. What that means is I can create 4 cascaded systems. I've got my input, produces x1. x1 then goes through a first order low pass filter, gives you x2, x2 gives you x3, x3 gives you x4. The output then is some linear combination of these 4 states. What that looks like in block diagram form is as follows. In matrix form, it's going to be x1 dot is minus p1 times x1 plus u. x2 dot is x1 minus p2 x2. x3 dot, I have all these cascaded first order systems. Then the outputs get added together to produce y. This is a better way to represent systems. Kind of go on the basis that simple is better. Simple systems behave better. Simple systems have better numerical properties than complicated systems. This is about as simple as it gets. I've got 4 cascaded first order systems. That has much better numerical properties. The difficulty, however, is you've got to sit there and factor out what are the poles. In addition, to get the numerator polynomial, it's a little more complicated. Essentially, a4 is just your constant over s plus p4, s plus p3, s plus p2 times s plus p1. a3 is the same thing, but I have essentially s plus p4, so the p4s cancel, and I have a3 going over cubic, a2 going over quadratic, a1 just is over s plus 1. To put this over a common denominator, I get this for the numerator polynomial, add all 4 of those up, and I get a polynomial. So this is a little bit more complicated to get to, but it does have much better numerical properties. That's Cascade Form. The last form we'll look at is called Jordan Form. It's also a Jordan or diagonal form. This has the best numerical properties and is also the hardest to get to. If I take my transfer function and then factor it using partial fraction expansion, I can treat this as 4 first order systems added together. So let's create 4 dummy states. I'll have this is x1, this is x2, x3, x4. All 4 of those x's get added together to produce y. In matrix form, it looks like following. This is a diagonal matrix. The input u affects all 4 states. Those 4 states have 4 weightings, and they all get added together to produce y. In terms of block diagrams, simple systems work better than complicated systems. These are 4 decoupled first-order systems. Can't get much simpler than a first-order system added together. So this has numerical properties, and by Murphy's law, this is also the hard to. So as a recap, In state space, the dynamics of a system can be written as x dot equals ax plus bu, y equals cx plus du, and you have a transfer function. A, B, C, and D can be expressed many different ways, actually an infinite number of ways. Some of those ways have names, like there's controller form, observer canonical form, cascade form, Jordan form. Many do not. It's all the same system, so you might think that they actually are related. So here's a question for you. What is the relationship between each of these forms? Well, it turns out the relationship is just a change in variable. Let's define a new variable z to be a linear combination of x. So z is t inverse of x times x. X is just some similarity transform t times z. For example, if my state x are three voltages v1, v2, v3, I could do a change in variable, saying z is v1 plus v2, that's your first state, v2 plus v3, v1 plus v2 plus v3. In matrix form, z is this matrix times x. This is the inverse of my similarity transform, T inverse. Now, if you have a similarity transform, I can just substitute. I've got x dot equals ax plus bu, substitute tz for x. There's your ax, substitute tz. Now, multiply on the left by t inverse. Gives you z dot is t inverse at times z plus t times u. That's the new matrix AZ and BZ. T is your similarity transform, and this is your transform space. So converting ABCD to AZ, BZ, CZ, DZ, I use the similarity transform. That's how Z and X are related. You're changing variable. And AZ is just T inverse AT, BZ is T inverse B, CZ is CT, and DZ is just D. Different canonical forms are related through change in variable, i.e. they're related through similarity transform. The easiest form to get to is Jordan form. Almost by definition, the transformation matrix that gets you there is the eigenvector matrix. So for example, if I have this system, that's your x dot equals ax plus bu, y equals cx plus du. To put it in Jordan form, I would find the eigenvalues and eigenvectors. So in MATLAB, here's your A matrix, B, C, D. Find the eigenvalues, eigenvectors. Eigenvectors is what I care about. My similarity transform is just the eigenvector matrix. And as a check, I can try it. In the transform space, AZ is just T inverse AT. That's diagonal. Exactly what you expect for Jordan form. My B matrix is inverse of T times B, C matrix. This is also where you can see observability, controllability, something we'll talk about earlier or a little bit later. If the B matrix is 0, that means the input can't affect this state. All the B terms are non-zero, so all four states can be affected. This is controllable. If one of these terms in the C matrix is 0, then I can't see that state. It's unobservable. All the C terms are non-zero. This is observable. So Jordan form tells you a lot. It tells you what the poles are. I have the best numerical properties. It's for decoupled first-order systems. I show the controllability matrix. I show the observability matrix. Pretty much the best of all worlds. So this is your system in Jordan form. Note about similarity transforms. Doing a change in variable doesn't change the system. Doing a change in variable doesn't change the transfer function. If I take my original system and find the transfer function, I get 1 over 4 poles. Take the system in Jordan form, find the transfer function, I get exactly the same answer. Similarity transforms don't change the transfer function. Second case, just for fun, let's look at the output and its derivatives. The output is just y equals cx. Take the derivative, x dot equals a times x. Second derivative, a squared times x. Third derivative, aq times x. So just for fun, let's make this the inverse of the transformation matrix. So t is the inverse of c, ca, ca squared, ca cubed. Here's t. Now find a, b, c in the similar the z state variable. So AZ is just the T inverse AT. BZ is inverse of T times B. CZ is C times T. So here's another way to represent the system. And note again, the eigenvalues don't change. Note again, the transfer function doesn't change. The transfer function in my original system, transfer function in my transform system. Finally, just for fun, let's do another change in variable. Let Z be x1 minus x2, x2 minus x3, x3 minus x4, and x4. That means that Z is this matrix, x1 minus x2, x2 minus x3, x3 minus x4 times x. If that's T inverse, then here's T inverse, here's T. Do your similarity transform, and you get something. Likewise for BZ and CZ. The eigenvalues again don't change. The transfer function doesn't change. So in conclusion, there are an infinite number of ways to represent a system in state space. All are related by similarity transform. Each transform system has the same eigenvalues. After all, the eigenvalues tell you the energy in the system. How you represent the system doesn't affect how the energy moves about the system. It may be difficult to determine what similarity transform that relates one system to another, but there is a change in variable, there is a similarity transform that relates two different representations of the same system. So that's lecture number 5 for ECE 463, Modern Control, Similarity Transforms, and Canonical Forms.